Till now, we learned that lots of functional groups can be produced from addition reactions across the double bond. Now, in this video, we are going to review a couple of ways that we can add two OH groups across the double bond to form a diol molecule. Now, as I mentioned, there are two ways that we can do such a transformation. The first way is anti-dihydroxylation. So during this process, as I mentioned, we are going to add two OH groups across the double bonds, but in anti-fashion. So we are going to add OHs across the double bond in the opposite sides. And in order to perform such a transformation, we need proxy acids. So let's look at this example. So this is our alkene. In the first step of this reaction, we are going to use proxy acid. So this is the general form of proxy acid. R group can change, but CO3H will not. So it is the same for all proxy acids. And the outcome of this reaction will be formation of a three-member ring, which we call epoxide. So this is an epoxide. It's a three-member cyclic ether, and if you remember, three-member ring is pretty strange, so it's very reactive and it's pretty easy to open epoxide. So in the next step, we are going to use some sort of acid to form a trans diol. So addition will be anti, and we are going to form trans diol. So since we form two chirality centers, we need to draw its enantiomer as well. As I mentioned in the first step of this mechanism, we are going to convert an alkene to an epoxide, and in order to do that, we are going to use proxy acid. So the general form of proxy acid is RCO3H, and we have two examples of them. Here are their structures. We can use either of them in this reaction. So the first one is proxyacidic acid. Here is the R group, 3 oxygens and hydrogen. And the next one is metachloroproxybenzoic acid, which is abbreviated as MCPBA. So majority of the time you will see MCPBA instead of the full name for this structure. So you need to know this name, and we don't have any abbreviation for proxyacidic acid. Now if you look at this structure, here is the R group, again 3 oxygens and hydrogen. Now let's look at the mechanism for this first step of this reaction. So in this mechanism, we are going to insert this oxygen in proxy acid between the carbons in the alkene. So if we follow electron pushing mechanism, the whole process is concerted process, and so many electrons are moving at the same time. So what we see is that 2 electrons from the pi bond in carbonyl will take the proton, and from there these 2 electrons between oxygen and hydrogen will form a bond to the top carbon, forcing a pi bond from here to form a bond between the oxygen and the bottom carbon. And then the electrons between oxygens must move on to this oxygen, but the best way to draw that is to move the electrons over this bond. And the reason behind that is when you move the pi bond From here, this carbon would get the positive charge. Now, to stabilize the positive charge, we need to form a pi bond here between the carbon and this oxygen. Now, let's review one more time that what bonds are breaking and what bonds are forming. So, the bond between oxygen and hydrogen is broken, and the bond between two carbons, the pi bond, is also broken, and the bonds between this oxygen and these two carbons are formed, and the bond between two oxygens is broken. And this is where we are going to form the epoxide. So the product for this step would be epoxide. So I'm going to show the stereochemistry here, but we know that we are going to form the basically dash isomer as well, because if the proxy acid added to the double bond from the top, we are going to form the wedge bond, and if it is added from the bottom, we are going to form the dash bond. But specifically in this example, it doesn't matter because it's a meso compound. We have plane of symmetry here, so it doesn't matter whether you show it in the dash or the wedge. Now, the next product that we are going to form in this step, so this oxygen will take the hydrogen, okay, and we are going to form a double bond between this oxygen and the carbon. So if you look at this structure, it is carboxylic acid. So it is just rotated in a space. Our CO double bond OH is a carboxylic acid, and this one is epoxide. Then epoxide wants to release the ring strain, so in the next step we are going to add some sort of acid to the reaction. So this is our epoxide, and we are going to add H3O plus. So oxygen on epoxide will act as a base and takes the proton from the acid. So this step is a proton transfer step, and we are going to form this intermediate. So this intermediate is even more electrophilic comparing to epoxide, and the reason behind that is because this oxygen is positively charged, and it eagerly want to get rid of that positive charge, so it will start pulling the electrons from the carbons toward itself, which makes the carbons even more positive. Therefore, in the next step, water will act as a nucleophile and will attack carbon and opens up this bond. So this is similar to what you saw with bromonium ion. Now, since the epoxide is in wedge, water will attack this carbon from the back side through SN2 mechanism and opens up the bond. So we didn't touch the stereochemistry of this carbon, so the stereochemistry here will still be in wedge. Therefore, we are going to form this product. So in top carbon, the stereochemistry is still in wedge. However, in the bottom, water attacks from the back, so we need to show that in dash. Okay. Now, to form the product, another molecule of water will act as a base and takes the proton from this intermediate. So it's a proton transfer step to form the final product. Now, since we formed two chirality centers, we need to draw its enantiomer as well. So this is how we are gonna make transdiol through anti-dihydroxylation. Now let's look at the example here. So we have this alkene. So first step MCPBA, and second step we are gonna add H3O plus. So when we see these reagents, we need to think about addition of two OH groups across the double bond in anti-fashion. So okay, so one of them in veg and in dash, and the other one must be in veg, because I'm forming two chirality centers, and also I need to draw its enantiomer as well. Now, how can we make a cis-diol? So there are a couple of reagents that we can use to produce cis-diol. So basically we are going to add two OH groups across the pi bond in a concerted mechanism, but through syn fashion. So this is our alkene, and there are two sets of reagents that can give us the same results. So we are going to form a mixture of enantiomers with both OH groups in the same sides. And I'm going to explain why do we get both enantiomers in the next slide. So let's look at the reagents that we can use for this transformation. The first reagent is osmium tetroxide with sodium bisulfite and water. And the structure for osmium tetroxide is this. And the next set is potassium permanganate with sodium hydroxide, and this reaction is happening in ice, so you'll see it is written cold on the arrow. And the structure for potassium permanganate is this. So we need potassium ion here to stabilize the negative charge on this oxygen. So we are not going to look at the entire mechanism for syn dihydroxylation, but we need to know that the mechanism is concerted. So OH groups will be added at the same time, and of course to the same side of the double bond. So in the first step of this mechanism, the pi bond will move over the oxygen, and that forces one of these bonds to break and move over the osmium. This forces one of these bonds to break and form a bond with this carbon. And this process will form a cyclic osmate ester. So we see that osmium gets a lone pair of electrons, and both of these oxygens are added to the same side. So the next step of this process is going to be reduction. So we are going to use sodium bisulfite and water, where we are adding 2 hydrogens to these oxygens to form the cis-diol. Now, if the osmium tetroxide added to the double bond from the top, we are going to form wedge bonds in the products. And if the osmium tetroxide added to the double bond from the bottom, we are going to form the enantiomer, where both OHs are in dash. So we are going to form a mixture of enantiomers. Osmium tetroxide is pretty toxic and expensive, so you really don't want to use a lot of that in the lab. So there is another set of reagents that we can use, but it still deals with osmium tetroxide. So we are gonna use osmium tetroxide again, but in catalytic amount, so a little bit of that, and we are going to use another reagent or co-oxidant which we call NMO. And here is the structure of NMO. Okay, this is NMO, and the result of this process is exact the same as before. So we are going to form a mixture of enantiomers and syn addition of 2 OH groups across the double bond to form cis-diol. But instead we are going to use catalytic amount of osmium tetroxide, so we are not using whole lot of toxic and expensive reagents anymore. So as I mentioned before, we can also use potassium permanganate with sodium hydroxide and in cold temperature to accomplish the same reaction and basically forming the same results. We are going to form cis-diol. The mechanism is exact similar as osmium tetroxide. However, potassium permanganate is fairly strong, so majority of the time organic chemists prefer to use osmium tetroxide with the co-oxidants such as NMO to form cis-diol through syn dihydroxylation.